All right, so coming back to the title of my talk, so I will cover all these different things one by one. So I'm a surface scientist. So the first thing I want to take a little bit what is surface science? What's my philosophical kind of view on it? Then metal oxides, which relates to the question of Sunil, you know, why are we interested in these kind of materials? I give a little bit of concepts that we have to know in order to understand this class of materials. Then I will talk about methods, and hopefully that leads into the latest results. I will introduce more methods as things go on, and that we need to discuss and to hopefully you appreciate our latest results that we've published in the last couple of years. All right, so surface science. My take on it is that I call it experimental modeling. So that means what one really wants to understand is surface chemical processes, surface physical processes, so processes, chemistry and physics processes that happen on the surfaces of materials at the most fundamental level, meaning at the single molecule, single atom scale. So we essentially want to know how, if like one molecule comes on the surface, how does it stick to the surface? How does it react? How does it change the bonds? The reason is, I will show you many reasons, but actually it's based so that there's already no one Nobel Prize in surface science, so no chance I will ever get it. Also for other reasons, I will never get the Nobel Prize, but there's one that has been awarded to Gerhard Ertl in 2007, who really introduced the surface science method to understand catalysis, so heterogeneous catalysis. And then if time goes on and if time's allowed and I'm not too slow, or if then I can tell you how one can use surface science to really understand heterogeneous catalysis at a fundamental level. Now, there is a list of other Nobel Prizes. So Walter Kohn won the Nobel Prize in Chemistry in 1998 for his development of density functional theory. So density functional theory meaning solving the Schrödinger equation, which for solids or for any sort of materials. And if you can solve the Schrödinger equation, which is very easy to write down, then you can essentially predict any of these properties. So for example, surface chemical properties and processes. So in density functional theory has a lot of approximations. The way it's done in surfaces is that you take a slab of a material. So you put the atoms where they are. You only need to know where the atoms sit, what kind of atoms and where they sit. And once you do that, then you can essentially calculate pretty much everything. You can calculate what is the lowest energy of the configuration, what is the electronic structure. If you put on a molecule, you can calculate where it would sit on the surface and how it will dissociate, how it will break apart. You can calculate all these things. But of course, that is approximations, and approximations means it may or may not be right? So these approximations are sometimes pretty coarse. So that's why one needs experiments to benchmark that. And the way we do this surface science experiments is experimental modeling. So that means they take very well-defined systems, so usually single crystals, where we know where each atom sits, similar to the DFT calculations, where we assume where each atom sits, so we can find out where they sit. And then we look at the structure, we look at the electronic structure, all these under low temperature, very well-defined conditions. So usually in ultra-high vacuum under well-defined conditions. So the upshot is that combining those two things, so experimental modeling and density functional theory, essentially these two Nobel Prizes, or what people developed in these two Nobel Prizes, we can really get very good insights. So that's what I want to show you today. And then the main thing are methods, right? So I promised you methods also in my talk. So the first method we will be talking about today is the one where Heinrich Rohrer and Gerd Binnig got the Physics Nobel Prize in 1986, which was for scanning tunneling microscopy, which as I will show you, is really uniquely suited to investigate the surfaces of these materials that we're interested in, these metal oxides. And then I'm not sure I get to this today, maybe tomorrow, about these other Nobel Prizes. They go way, way back, that has helped us develop these techniques to really get insights into surface chemical properties. All right, enough said. Why metal oxides? Answering these questions. So they're very robust, they're abundant, they're everywhere, they're very versatile, and used for many, many applications. So I already mentioned heterogeneous catalysis. We have a catalyst that's usually some sort of spongy material, high surface area, and there's some small metal particles on top of that. These small metal particles are the ones that catalyze a reaction. For example, oxidizing carbon monoxide that's poisonous in CO2, or what people are now very interested in, looking at the opposite. How can you get CO2 and then put a hydrogen on top of it, or add hydrogen to it and make methanol out of it, which would be a fuel. So all these things can happen, and this happens and with catalysts you can accelerate this reaction. So that's heterogeneous catalysis. That was one of the main driving forces really for developing this method, and that's also where Gerd Erdner got his Nobel Prize. There's many others. So you can do this heterogeneous catalysis with the help of photons, and it's called photocatalysis. So that's a very nice, a nice slide that I've been showing for a long time. So TO2, for example, is a good photocatalyst. These are 3 bags filled with latex particles, and they're coated with TO2. Someone put here, it's unfortunately mirror image, it's coffee. Someone put coffee stain on these TO2 particles. I'm sorry, TO2 particles that coated with TO2. And then if you expose it to UV light, then the coffee goes away. Okay, the coffee is photocatalytically oxidized to its organic molecules, CO2 and water. So, being a mother of 2 now grown boys, I was very interested in this research, right? Because it's very nice not to do laundry anymore, just go in the sunshine and then your coffee stains go away. There's many other things. So solid oxide fuel cells, where one uses a chemical reaction to gain energy, very novel type of electronics. Another one is very interesting properties. For example, one of these materials that we're talking about today is a transparent optical conductor. So on my screen, on your screen, everyone, there is this indium oxide coating. Okay, so many, many applications. We could go on for hours, how many? In virtually all of them, the surfaces and interfaces play a role. Very clear in heterogeneous catalysis. For these interfaces here, if you have a screen, then what you put next to it, the interface really matters. So understanding the surfaces and interfaces at a very fundamental scale gives this impetus for doing these things, but really we are very, very physics, chemistry oriented, really want to understand the meaning, being able to do experiments that you can model and theoretically and therefore really understand. All right, so metal oxides, if you're a surface scientist, is actually a very logical thing to look at metal oxides, because if you look at the periodic table and you just look at elements, these are the elements that are metals, essentially almost everything that's not a gas or some sort of semiconductor. So a lot of things are metals. If you expose it in the ambient, then I unfortunately have used yellow here. It's probably not so easy to see, right? So you can see pretty much everything becomes oxidized, maybe not gold or mercury, the very, very noble type of metals. So virtually everything has an oxide on top of it, right? So oxide means it's not just oxygen adsorbed, sticking to it, but it's really reacting with it, and the oxygen is incorporated in lattice. You have a metal in the oxygen. So many, many oxides are possible. These are the ones that have been investigated by the surface physics group at TUV, so my group here. The ones in blue are what we call simpler binary oxides, so just titanium oxide, iron oxide, indium oxide, and those are the ones that I hope to cover in this lecture. So it's very simple, just one element, one oxygen. And then there are relatively simple rules how to look at these surfaces. And I want to get to that to show you how one can predict what surfaces are stable. and one will encounter in nature. So if there's also, I should mention, there's also, of course, you can combine different metals. For example, you could combine strontium titanium and get strontium titanate, or potassium and tantalum, it's here, and we would get potassium tantalate. Once you do that, things become way more complicated. I will not talk about that today. If ever I have to give another lecture, I could talk about these aspects as well. Okay, so these are the ones that our group has investigated on the surface. Who is our group? So this is the research group. Every year in July, that has been tradition for the last 10 years, we go on the roof of our building. We line up here. In this case, we had 2 meters distance because of Corona. We take this picture very far away with this strong lens, so it looks like we're right next to the Stephansdom, which is right smack in the center of Vienna. So actually, door to door from Setek to here, it's 2 hours. So I think things have been relaxed. Corona rules have been relaxed. So if any one of you wants to come and visit the lab, I would be more than happy to show you around. So most of the people here, students, postdocs, my colleagues, also Professors Michael Schmid and Gareth Parkinson, they are experimentalists. We have a few theorists, but mainly we collaborate with people doing this density functional theory. So there's a very strong group in Vienna by Georg Resse and Cesare Franchini. And then one of the results I will show you is together with this person, Bernd Meyer in Germany. And this guy, Martin Sedwin, used to be part of a group and is now a professor in Charles University in Prague. And I should mention the funding, especially, of course, the SINSE project, which, makes me to give this lecture to you today. All right. So far, so good. So, outline of the talk, again, concept of methods. First, I want to talk a little bit about how we can understand these oxide materials. So when oxygen and a metal makes a compound, and then what are the rules to make sure that we look at the right kind of surfaces, right? When you take a material, you make a surface, you can essentially in your head cut it, or in real life cut it in different directions, and then depending which direction you cut it, it could be more or less stable. So we'll talk about that. And then I already mentioned that all our experiments are done in ultra-high vacuum, and then I will talk about how one can use and how useful scanning probe microscopy is to investigate these materials. All right. So metal oxides. We need a metal and oxygen, right? Okay, then we have a metal oxide and they combine, they really form a compound. They make bonds with each other. And since oxygen is a very electronegative element, and most metals are more electropositive, what will happen? What will happen is that the oxygen sucks away electrons from the metal, right? And will become closed shell, so it misses 2 electrons, so oxygen 2 minus, and then becomes an anion, and the metal becomes a cation. So virtually all the oxides, in all the oxides, we can, at least from a formal point of view, say the oxygen has 2 extra charges, and then depending on the stoichiometry, the metal has positive charges, right? So actually, the way it's drawn here is not quite true. In reality, this oxygen is actually much bigger, and this cation is much smaller. So this is a more realistic picture. So here, this would be an oxygen, 1.2 angstrom radius, and this one would be, can you see this? Yeah, this would be a cation, 0.7, right? So the oxygen is big, the ionic radius, because it has the extra electron, and the cation is small, right? So oxygen big, cation small. And because in metal oxides, because the electrons are at the oxygen, the electronic structure would look like this. So this would be in an oxide material, this would be the density of states, the number of states of the electrons in the material. This would be the binding energy, the energy they have. It's filled, so you have a band gap usually. So you have filled states and empty states. Filled states valence band, empty states conduction band. And then normally if you have a band gap in between, so many of the ones I will talk about have a band gap of about 3 electron volts. So actually the indium oxide and the have about 3 electron volts band gap. And normally from a formal point of view, in density functional theory, the Fermi level, you would put the Fermi level right in the middle of the band gap. But experimentally, what we have is we have the Fermi level at the lower edge of the conduction band. And so all the metal oxides essentially have the Fermi level at the lower edge of the conduction band. So now comes my first question, Rojana.
Yes, I will just shortly run the poll.
Okay.
So what do you think? How much time should we give them for this
a minute.
question? A minute?
Yeah.
Okay.
It's a hard question, I think. I hope. Actually, it's anonymous. So you can, if you give a wrong question, we will not find you. Yeah, half a minute.
Half minute down.
Okay, sure. Good. Okay, that's it.
Now 20 seconds.
All right. Maybe we can stop already.
Yes.
Let's stop. Oh, we cannot stop. The poll is ended. So what was the answer, Rojana?
I'm just waiting for the reminder of the
Okay.
answers to come in. So you should be able to see the results.
N-type.
I'm sorry?
Okay.
Yes. The N-type.
Can you start my video again?
Yes,
I will. Can you let me share again? Okay.
Let you share again.
Okay. Right. Okay. So the question was, it's N-type and it's too much so it's actually too little oxygen. It's completely wrong what I have here. So actually it's too little oxygen and it means reduced. So forget this. This is all wrong here. So the answer was actually it's N-type and it's too little oxygen. Actually, that means it's reduced. Okay. So basic building blocks.
You have to share again, please, Ulrike.
Huh?
You have to share again the presentation.
Oh, I haven't shared yet. Sorry, I haven't shared. Rojana, I don't share. What? Fine. So the answer is it's N-type and it's too little oxygen and it's reduced. So basic building blocks. So all the oxides consist of really simple building blocks. So you have a metal in the center, and then you have surrounded by oxygen. So here, what we call octahedron. So octahedron actually means 6 oxygens. So 1, 2, 3, 4, 5, 6. So 6 oxygens is very common with one metal in the middle. So there's an oxygen on all of these corners. Okay. And the other one is tetrahedral. So we have an oxygen in the center. We have metal in the center. We have 4 oxygens on each corner. 1, 2, 3, 4. And the reason is just, as I showed you, maybe I can show you again here, when we have close packed oxygen lattice, you put a metal in the center. We put another 3 on top. We can get something like, this looks like an octahedron if you do it right. Can you see this, Hansa? Can you see it? Can you not? I can see you. Okay. So it's an octahedron. And then a tetrahedron means you have a metal in the center and you put one on top. So you have 4 oxygens. You can see it's a tetrahedron of 4 oxygens and it looks tetrahedral if you rotate it right this way, for example. So those are the building blocks. Okay? And the oxygen, as I mentioned at the beginning, they are really big. And then they can have all sorts of complicated structures. So you can put this octahedron together and they can share an edge. You can put them together and they can share a corner, this octahedron, tetrahedron. And with that, you can make all sorts of really complicated structures. They look really complicated at first sight. So all these oxides, many minerals are oxides. If you look at the crystal structure in the beginning, it looks really mind-boggling because they look so complicated. But if you look at them, it is really, you know, put them in building blocks, this octahedron or tetrahedron, one can kind of understand them. Even better if you're a surface scientist, and you can think, then we think in terms of layers of surfaces, right? So these oxygen ions, as I said, are really big and they form a closed packed lattice. So closed packed lattices, so you can see red is oxygen, you have closed packed lattices, meaning octahedral, hexagonal closed packed. Here another lattice, another layer, and in between are these small cations. Then these small cations, if they have 6 neighbors, they're octahedrally coordinated. If they have 4 neighbors, they're tetrahedrally coordinated. So in terms of surface science, you can think of them of having these closed packed lattices, oxygen, really big, and small cations in between. Okay, so TO2, my favorite material, I've published a lot on this. So this consists of titanium, which is 4+, right? Because it has 2 oxygens, so it has given 4 electrons away to the oxygen 2-. And if you look at this titanium atom, for example, sorry, let's look at this titanium, for example. Titanium atoms, it has 6 neighbors, 1, 2, 3, 4, 5, 6. So it has an octahedron. Then this titanium atom here has also 6 neighbors, 1, 2, 3, 4, 5, 6. So again, an octahedron that's this way oriented. And you can see they share a corner. That means they have 1 oxygen in common. Boże, now if we do this drawing, can one see it or is it a delay? Okay, perfect. So this is what we have now. When we want to create stable low energy surfaces, so if you cut the material in half in one specific crystallographic directions, then in order for these surfaces to have low energy, which means A, they're stable, and B, they're very common in nature, so those are the ones we really should look at. There's a very, very simple rule for these simple binary oxides that I talk about, TO2, indium oxide, and so forth, with only 1 oxidation state of the cation. There's the caveats, but the rule is really simple. The number of broken bonds metal to oxygen should equal the number of broken bonds from oxygen to metal. Okay, so you have the same number of bonds, you break the same number of metal to oxygen as oxygen to metal bond. So here you can see this TO2 again. So I break 1 bond from metal to oxygen here. And then here I break some oxygen to the metal. And here I break 1 bond from metal to oxygen if I make a cut like this. Right? So here are oxygen to metal to oxygen bonds are broken and make a cut like this. And this will give me a surface that's very low in energy. Okay? And that's really true. So actually, this is how this surface looks like. So the surface then has left over these titanium atoms that miss 1 partner. So they have 6 octahedral in the bulk. Now they are 5-fold coordinated. This oxygen actually had 3 partners in the bulk. Missing 1, the oxygen are 2-fold coordinated. Okay, and these we call this so-called bridging oxygen atoms. So it's really powerful, actually. You can even predict how steps look like. So this is on this TO2 surface. So we have these oxygen atoms, the titanium atoms, oxygen atoms sticking out. And they can see how these different, this is how one from the simple rule predicts how a step would be oriented in 1, 1, 1 direction. And this is the STM image. You have these rows of the 10 oxygen atoms. And this is the steps that you can see. All steps have similar orientation. They're all in 1, 1, 1 orientation. Okay, so it's really, if one asks you, okay, here's a binary oxide, which surface is stable? The one where projecting the same number of oxygen to cation and anion bonds. The first approximations, there's always more complicated things. Okay. So let's go to this other material that we'll talk about, indium oxide. I'll tell you in a second why it's interesting. So in the bulk, it looks really complicated. So this is the unit cell. It's a cubic unit cell. It has 1 nanometer lattice constant. So it's a cube 1 nanometer in size. That's really big. Inside of this cube are 18 atoms, 32 indium oxides that are 6-fold coordinated. 6-fold coordinated meaning octahedrally. And then 48 oxygen atoms that have 4 nearest neighbors, 4 octahedrally coordinated. And then if one cuts it in 1, 1, 1 direction, this is how the surface looks from the side. You have indium and oxygen. Unfortunately, this is drawn wrong. So the indium is actually big and the oxygen is small. It should be the other way around, as I told you. But you have layers of indium, oxygen, and indium. And then the main thing is that on the surface, you have a really, really large number of atoms. So you have 40 atoms just in the unit cell on the surface. You have 4 indium atoms that are 6-fold coordinated, 12 that are 5-fold coordinated. And what will be very important later on, we have 12 different types of oxygen atoms, 12 oxygen atoms that are all surface atoms, and many of them have a different, slightly different coordination. As we'll show you in the end, hopefully today or maybe tomorrow, all these oxygen atoms here that are 3-fold coordinated, they have a slightly different surface chemistry. Okay, so this is a really strange material. It's really complicated. It has a big unit cell. Why would one be interested in? Actually, this one, indium oxide, is the one that is a transparent conductive oxide. So it has a band gap of 3V, which means visible light can go through. And if it's stopped with, and still it's really well conductive. So indium oxide, when topped with tin, has a really high conductivity, almost like a metal. And that's what you want for a screen, like for your computer screen. The computer screen here needs to be conductive, or a touch screen needs to be conductive, yet it needs to be transparent. So, okay, now comes the second question. Let's see how many people answer this time. Most materials with a metallic conductivity, so if you think of any metal, okay, copper, iron, all the ones that I mentioned at the beginning, right? They're all metallic, meaning you can't look through them, right? They really absorb light. And then we have insulators, rock salt, for example, right? Transparent, has a wide band gap, doesn't conduct at all. Aluminum oxide, right? Transparent, sapphire, wide band gap, doesn't conduct at all. Now, indium oxide is both. It's conductive and transparent. And the question is, how come? How can that be? So, Bojana, please post some questions.
Okay, it should be posted.
Okay.
So I hope this time we will get
answers.
Yeah, like it's not easy for everyone to answer because some people who are connected through phones they can't.
I
think
see.
this poll, but
Ulrike,
usually
can I
at
ask
least
you? Can I ask you a question? Here is Pavel
Sure.
Kuchak, a biologist.
Huh? What?
A biologist. Okay.
Biologist.
A
Okay.
biologist. We
Yeah.
talked to each other a couple of weeks ago.
Yeah.
It's very difficult to answer these questions because I don't know what is a S-like state. I don't know what is a doped semiconductor, and I don't know what is a conduction band.
Okay.
So
Okay.
vast majority of the terms here, I don't know.
Okay.
Is there any
Yeah.
possibility to give a brief summary of what seems to be very well known in material science?
Yeah, sure, sure. I would be very happy to do that. Very happy to do that, actually. So I didn't know, right? I don't know who normally ask the audience what their background is. So if biology, then of course this is really difficult for you. I understand that.
I'm probably unique here, you know, so I'm sure that the others know. But if there is
you shouldn't overestimate people.
if there is 1 minute to define these terms, it would be great.
Yeah, okay. Actually, I will give you the answer in a second.
oh, last few seconds, and I'm
Okay.
closing the poll now. So
All right.
let's hope everyone will submit their results.
Okay, and they need to share again, right? Last time I made this.
Last time, just 5 seconds till the poll runs out, and then you
All
can
right.
share again. I will share the results of the poll with you as well. So there's the results. I think that
Okay.
yeah,
Right.
that's the very much split answers on.
It's a split
this one.
answer. Yeah, it's split answer. Okay. All right. Yeah, I'm happy to spend a few minutes on this. So, first of all,
you can share again.
Sorry, I'm stupid. Share. Okay. So I asked, and I will tell you in a second what this all means. It has S-like states in the conduction band. It is a doped semiconductor. It has a band gap in the conduction band. And actually the answer is it needs all of the above. So what is this? This here is for the solid state physics people with this, physics background. This is something they know. For biologists, what you maybe know is, Doman Chak. What's your first name?
Pavel.
Pavel. So Pavel, right? You know molecules, right? So molecules have, if you have a molecule, you have a highest occupied molecular state and the lowest unoccupied molecular state. You know this concept, right? So you have molecules, you have orbitals, and then some orbitals are filled and some are empty. So this is the same thing in solid state physics, that you have some orbitals essentially that are filled and some that are empty. So this here is the energy of the electrons in the solid. Never mind this part for now. So just these are the energy. The electrons, so let me get to this.
I think it would be helpful, the schematic which you had previously in the presentation about the Fermi energy, that's where I got lost.
Okay. So you
Rest
have
is very, very clear.
Okay, perfect. So you have here the empty states and the filled states and the empty states, right? So for a molecule, we have here the HOMO and the LUMO. And if you have an optical oxidation, then you take an electron from here to here. So a photon comes in, you take an electron, you get it from the filled states to the empty states, and the photon is absorbed, right? That's the absorption. Now, if something is optically transparent, that means that the photon energy is not high enough. So you cannot take an electron from here to here, right? So for something to be optically transparent, it needs to have a band gap, or it needs to be a semiconductor. So that's for sure clear. So optically transparent needs a band gap. You can see here is a band gap between, these are the filled states, these are the empty states, right? It's a band gap in between. Okay. Band gap is 3V, no visible light absorbed. Now for something to conduct, you need to put some dopant in. So you need some electrons here. So here the electrons cannot conduct, they cannot go from one orbital to the other one because there's Pauli principle, there is no other state available. You have to put them into the empty states, a few electrons, you have to dope them. Okay?
What does dope mean?
Doping means adding an impurity. Or taking out some, or so in some way making it, changing the electronic composition. So adding electrons or taking away electrons. Adding electrons in N-type dope, taking away in P-type dope. Okay. So for example, for this indium oxide, we dope it with tin. And I don't have the periodic table here now, but tin is right next to indium, has one more electron. So the tin gives up some electrons, so it becomes what I call N-type doping. So the electrons go all in the empty states. Okay, so we have to have some doping, we have to add some extra electrons for it to become conducting.
Okay.
And then now this goes to this S-like character, and for that you need a little bit solid state physics. So these are the bands, the way the bands are. So these are what's called dispersion relation. If you just look at electrons that can conduct really well, they have this type of, so this is the momentum and this is the energy. They have this type of dispersion. Okay. So I will not go.
That's enough. Yeah.
Yeah. Okay. That's the S-like state. So they are conducting. So this is the dispersion. Now, most materials, like when you take TiO2, I will show in a second, when you put dopants in, they become dark. Okay? Because now you have electrons here, and these electrons, when you can shine a light now, these electrons will go from here to here. So the electrons can be excited from here to here. Right? So they become dark. You put enough electrons in here to conduct really well, 10 to the 22, 10 to the 20.
Okay.
Then the thing will start to absorb light. Right? Because these electrons absorb light. Now, what happens is that here in this indium oxide, if you look the normally empty states here, there's another band gap. See, from here to here. So these electrons that have dumped in here, when you now put light, they cannot absorb. They cannot absorb the light. There is another gap.
Okay.
Okay. So, all right.
That's very clear. I have one control question. When you dope something, does it mean that you actually add the tin, like few atoms of tin into the material? That's what I should understand it?
Yes, exactly. For example, for indium oxide, one puts 10% tin.
Okay. Clear. Perfect.
Right.
Thank you very much.
Perfect. So
we can move on.
All right, perfect. So a material to be optically transparent is a doped semiconductor. It has a band gap and it has doping. It has an S-like states, conduct easy. Those are the ones you put electrons in. Some get stuck, some not, and has a band gap in the conduction band. Okay, perfect. So good. All right. So coming back, I talked about oxide materials, oxide surfaces. I tried to convince you they have all sorts of applications. We talked about cutting bonds to make surfaces. They're also insulating. And then, so this doping, okay, so you can either add foreign elements, like the tin, for example, or actually the easiest part is also to change the stoichiometries, they change the composition. So one is called extrinsic, meaning adding tin, for example, right? So you really add something. Or intrinsic doping means they're not perfect. So like for TO2, right? For example, take a little bit of oxygen out. A little bit of oxygen out, it also puts electrons in. So that's what we call intrinsic doping, and that can change the electronic structure. All right. Any other questions so far? Thank you, Pavel, for this one. All right, then let me move on. Then oxide surfaces. So now we talk a little bit about methods, okay? I haven't talked about methods or techniques right now. So why we need ultrahigh vacuum? What kind of samples do we have? Defects, small imperfections are really important on surfaces, I will show you. And scanning probe microscopy, if you operate it right, is really nice way of looking at these surfaces very directly. So all the experiments we do are super expensive because we do them in ultra high vacuum, UHV, meaning we do them in these stainless steel chambers where you have also wonderful facilities at CETEC. We don't do it because it's much fun. It's not fun because it's not easy to operate. It's lots of technology. It's super expensive. But we need that to keep our surfaces clean, right? If you have such wonderful, great surfaces and you put them in the ambient, they're covered immediately with dirt. So for ultra-high vacuum surface science, we have this figure of merit. If you have here a pressure of 10 to the minus 6 millibar, so 10 minus 6 millibar, 1 atmosphere is 1 bar, right? So that's 1 bar, millibar. So that's 10 to the minus 9 atmospheres, or 1 parts per billion of some molecules in your vacuum or in air. If you expose it to a sample for 1 second, it's covered completely with 1 molar of dirt. Right? So that's why we don't go to 10 minus 6 millibar, we go to 10 minus 11 millibar, because then we have 10 to the 5 seconds to do our experiments. So everything we do is in ultra-high vacuum. Everything we do, we use single crystals. So this would be a metal single crystal, a platinum single crystal, mirror polished to a very shiny surface. And we like to use, and that will be the next part, so I'll talk scanning tunneling microscopy. So if you look through this microscope, optical microscope on an ultra vacuum chamber, you look inside, you will see the sample on a sample holder. So this is about 5 millimeters diameter. Here is the tip, the very end of the scanning tunnel microscopy tip, fine needle, and it's mirror polished, so you see the mirror image. Okay, before I go to this scanning tunneling microscopy, let me talk a little bit about samples. So the samples, I talked about this indium oxide already a little bit. I told you it's optically transparent. Actually, it's a little bit yellowish. And the reason is just that even though it has a 3 band gap, there is some Urbach tail there. So there's some optical phonon excitation. So well, we're not going to these details. But anyway, even though it's still, you can still look through it, still pretty shiny. So these are indium oxide single crystals. This is a typical size that we can look at, so this is 5 millimeters, 2 millimeters or so, they're all very nicely oriented in one direction, crystallographic direction, and they are usually polished, so they're really nice and smooth. We get them by, in this case, by a person who has a friend who has grown them with vapor phase deposition, vapor phase growth. We also grow our own samples with pulsed laser deposition. TO2, I had this question at the beginning, why are we interested in TO2? Actually, another reason is it's really easy to handle, right? So this, you can buy single crystals, pretty cheap, $100 per sample or so, in any sort of orientation. They're hydrothermally grown, which is a relatively inexpensive growth method. If you buy a single crystal of TO2, it's optically transparent. It has a 3V band gap. Electrons can be excited from the filled valence band to the conduction band. We treat them in ultra-high vacuum by cleaning them, by sputtering and annealing. Oops, sorry. And then what you can see is once we take out oxygen, we dope them, we take out oxygen, put in, that leaves behind extra electrons, it becomes opaque, it becomes really dark. So this one doesn't have this nice property as the indium oxide. But if we just put a little bit, if we just reduce it a little bit, take out a little bit of oxygen, they become light blue, and they're pretty conductive already at room temperature. So this TO2 single crystals, indium oxide single crystals, and then we also use, I don't know if I get to it today, iron oxide single crystals. So again, this is always the sample holders we use, so 5 millimeters. They are actually the easiest one because magnetite, iron oxide, is really most abundant element or minerals or element or compounds on Earth. So if you look and try to buy, it's called lodestone. It's a natural magnet. You can buy it Amazon.com really cheaply. Huge single crystals actually. Rare earth for sure not, because iron is not a rare element, but it's pretty cheap. So actually, there's this one company that we have been buying these natural mineral crystals. They buy them from mineral sample shops and then cut them and orient and polish them, and then we get them and then we use them for our experiments. Okay. All right. Now let's talk about TO2 next. And let's look at this, how we can use scanning probe microscopy. So scanning tunneling microscopy and atomic force microscopy to look at it. So this is the end of the sharp needle that I've shown you. It's in what we call tunneling contact. So a few angstrom, half a nanometer in front of the surface. We have a voltage between tip and samples. We have a tunneling current. We keep the current constant. And we gently stroke the surface back and forth, and this motion of this tip will be then transferred into a image. So that's scanning tunnel microscopy. I assume most people know about it, right? I hope. Anyway. So the other one is non-contact AFM. Probably many people, even biologists, use non-contact AFM, atomic force microscopy. But the way we use it in ultra-high vacuum is a little bit different. It's a similar concept, but a little bit different technical setup. For both scanning tunnel microscopy, so the real signal that we measure is actually, the tunneling current between the tip and the sample. And here, what we measure here is, this is a, you can see this from here to here to here. That looks like a tuning fork, right? So a tuning fork has its own resonance frequency. So we use it for having 440 hertz to swing it, and then it goes, it resonates with one single resonance frequency. And on here is also a little tip mounted, and we measure the change in the resonance frequency F for the scanning probe microscopy for non-contact AFM. So in one case, we measure the current, we use scanning tunnel microscopy, or we measure the change in frequency when we bring this tip and the sample close together. Okay, now let's look at pictures of this tier 2110 surface. So this is the surface I showed you before, where I cut the metal to oxygen and oxygen to metal bond. Remember, we had titanium atoms that are 5-fold coordinated. We have oxygen atoms that stick out a little bit from the surface. They have 2-fold coordinated. They miss the titanium neighbor on top. And the way we treat them, and that's why people like to work with this material so much, the way we treat them in ultrahigh vacuum, we always take out, so when we make them a little bit blue, okay, but they're blue because we took out some oxygen from the sample. And actually the oxygen we take out are all these oxygen type, the same type. So these ones that are these bridging oxygens, the 2-fold coordinated. We have made here some oxygen vacancies. So this is what we have, this is what you get out of one of these theoretical calculations. This would be a very stable surface. This is the most common imperfection, defect, an oxygen vacancy, a vacancy at the position of the oxygen. And if you look at non-contact AFM, if you look at the frequency shift, that's exactly what you see. You can see here oxygen atoms aligned in nice rows. And some of them are missing. Those are the oxygen vacancies. So we can actually see, directly see these defects. Now, when you, it turns out these are very new results, actually. So this is from 2017. The last 4 or 5 years, people have started to use this non-contact AFM on oxides. It's a wonderful technique because you can directly see these oxygen vacancies. For the past 25 years, people have been using scanning tunneling microscopy. So they just looked at the tunneling current. And here, right, we have the tip and the sample. Tip and the sample. And we measure the current between them, and the current can go 2 directions. It can either go from the tip to the sample. This is when the sample is positively charged. Or it can go the opposite. It can go from the sample to the tip. This is when the sample is negatively charged. And then we see different things. So when we look at this, so this is exactly the same area on the sample. So we have these rows of oxygens, we have these rows of titanium in between, and we have these oxygen vacancies. In empty states here, so when we tunnel from the tip to the sample, stuff electrons in, there is no states available into the empty states. You can see here is an oxygen vacancy. We see a bright spot. The reason is just that the empty states, so the unfilled states, have changed a little bit. The orbitals have changed a little bit, but it's not really an atom here. It's just a change in electronic structure. So let me show this maybe in the next slide. So
can I ask a quick question? What
Sure.
is the, in this image, what is the difference? What does the difference in intensity mean?
Okay. So in this case, in all of these, or in one,
Well, I would say in both of them, because the differences in intensity appear in both techniques, right?
Yes.
I would somehow naively think that they will be binary. Either there is an atom or not.
Yes, exactly. So for example, so here, this is the change in resonance frequency. I don't have here how much it is, but here, so the change in resonance frequency, okay. I will talk about this one first, but here means, so I showed you before how this tip goes up and down, right?
Mhm.
So when the tunneling current is high, we keep the tunneling current. So actually in this case, this is a constant height. So we go across the tip like this, and you just measure if there's current possible to go in or out. So whenever there's a titanium atom, right? Titanium, let me show you the next one. So titanium, maybe this becomes clear. So you have the Fermi level we set here. You bias the tip with we bias the sample with plus 1.2 volts. So that means the tip sends electrons into the sample, but it can only send it into these empty states, right? And then when we move the tip across the sample and keep this current constant, so we put the sample tip here, we have it in a certain current, certain tunneling current. We move it in X direction, then we come across this oxygen atom that sticks out a little bit. Here, locally, we have the oxygen states. Oxygen has no empty states, so we cannot put any electrons, so we have to move closer with the tip to keep the current constant or less electron states. And we move back again. Here on top of the titanium atom, here is more possibilities for the electrons to pump back in. So if more empty states. So here the tip moves back. So it moves up and down. When it's on top of an oxygen, it moves up. When it's on top of the titanium, it moves down, up, down. And here, where there is an oxygen vacancy, these empty states are disturbed. So we have more empty states available. So here the tip moves even higher up.
Yeah, I completely understand where the contrast comes from.
Okay, right.
Difference when you are on top of oxygen and when you are on top of the metal. That's very clear, right? These big differences. But there are small differences among the oxygen atoms.
Here.
And that's what I don't understand. Why are they there?
Here on top of the oxygen, here, you mean?
Yeah, like
here.
for example, if you look at in the non-contact AFM, for example, there is a row of oxygen atoms, which are bright.
Yes.
And then there is one next to it, which is not so bright.
Yeah. Okay, this one is,
yeah.
This one is relaxed downwards a little bit. And also, we think that's what it is here. This one is relaxed down. So this,
and does that mean that it's relaxed down? It means that it changes in position?
Yeah, it's very sensitive to the position. It's a little bit higher, a little bit lower, a little bit higher, a little bit lower.
Okay, that's super clear. Yeah.
All right.
Okay, and then when there's one missing, then there is no signal. Clear.
Yes, exactly. That's very easy to understand, right? There's no signal. Here, there's signal when there is something missing. So that's always.
Yeah.
Now.
Thank you. I'm done.
Okay, actually, I'm not done. Yeah, there's one more thing. So if you look at this one, TO2, and you look now at the field state, so we have the sample negative, and we take electrons from the sample to the tip. Okay. And the bias voltage here, the voltage is 1.2 volts. Right? So that actually one of the more interesting occasions. The tell you why. So for TO2, I told you we have a 3V band gap. The Fermi level, that's the reference level, is here. So we have here, we look at these states when we have a negative bias voltage of 1.2 volts. So we shouldn't really see anything. Okay. The reason why, because there's no states in the band gap. There's no way to tunnel. The reason is we have these oxygen vacancies here. So you take out an oxygen, right? I told you in the beginning, oxygen has 2 electrons. You take out a neutral oxygen, it leaves behind 2 electrons. And these 2 electrons actually like to go down. And we can tell from our images together with DFT calculations, these 2 electrons like to sit in the, not on top of the surface, they like to sit on a metal, on a titanium atom, but not on top of the surface, in the next row below, underneath. And actually these electrons then can hop from one to the next, to the next, to the next. That's the conduction mechanism. And these electrons, these extra electrons, make this band gap state. So this state that we've seen before is because of the electrons that are left behind when an oxygen is removed. We make this oxygen vacancy, put extra electrons. These extra electrons make this extra state in the band gap, and they're actually located underneath in titanium atoms underneath the sample. So this is the schematic I showed you, right? Valence band, filled states, Fermi level, conduction-based states, empty states, band gap. So this is the blue are the calculated density of states. You can see there's a very nice sharp feature. Those are these extra electrons that are left behind and put into the sample because you remove oxygen. Here is the reference level, the Fermi level at 0. This is the conduction band minimum. These are experimental spectra by parking the tip on top of the sample and ramping the bias voltage, positive and negative voltages. One can measure this gap state. One can determine this state. And it agrees quite well with these DFT calculations. Okay. And if the theorists, so this is collaboration with Michele Reticcioli and Cesare Franchini and Georg Resse, the theorists put the electron into the sample. So this is a row of titanium atoms at the surface, a row of titanium atoms in the next layer down. If they put extra electrons that come from this vacancy, the most favorable condition is here, underneath, in the second layer. And there's a little bit of orbitals of density of states reaching out. So these are simulated STM images of one extra electron in the second layer. You see this double lobe feature. These are simulations, and these are, you can see the electrons in the filled states, these gap states. Okay. Now, I don't want to go, I could talk about this, so about these extra electrons in lots of detail. Actually, we've published just a paper here this year in Nature Review Materials. We just talk about these extra charge carriers, because these are what people call polarons. So these are quasi-particles where charge carrier, an electron, hops from one side to the next, to the next, to the next. And then if you have in a lattice, in an ionic lattice, you have a metal, you have an oxygen, metal is positive. You put an extra electron here, extra electron will push away the negatively charged oxygens, and attract a little bit the positively charged titanium atoms. So there's a distortion. There is distortion in the system. right? You put an extra electron around it, the ionic lattice reacts to that. Extra electron, negative oxygen pushed away, positive deuterium pulled here. So there's like a distortion cloud, polarization cloud that is in the lattice. And when the electron hops from one side to the next, it takes this cloud with it. And depending on how strong it interacts with this lattice, that determines how easy it hops from one to the next to the next. So that matters how well the system conducts. It matters for the optical properties, it matters for the chemical properties. So these electron-phonon interactions, or this interaction between an electron and ionic lattice, is really a very active matter of research that we have discussed in this paper. I will not go into details, but the nice thing is that with STM, with field state STM, one can actually kind of unsee the effects of these polarons, the effects of these electrons that are gap states that are really important for the properties of these materials. Okay.
May I ask to understand it a bit more deep? So you have the original oxygen vacancy, and it gives rise to this polaron.
Yes.
And it can hop only to the vacancies or just to any other side?
Ah, that's a very interesting question, actually. So if you look, so this is why this picture is so important, right? We know here, this is exactly the same area. We know here it's the oxygen vacancy. We can see the oxygen vacancy and the empty states very clearly as a bright feature, even though there's no atom. Now, in the filled states, right, where you can see there's nothing. There's nothing here, there's nothing here. Nothing here, nothing here. So the electron, that's what I try to do here. The oxygen goes away, it leaves the electron behind, but the electron doesn't stay in the vacancy. It moves to the next deuterium atom and localizes there.
Yeah.
Okay. Now, one question is, if it localizes there, right? If it just, so what, coming back to the question of Pavel, here, what we can see is electrons that tunnel from the tip to the sample. Oh, sorry, from the sample to the tip, right? And whenever something is really bright, it means there's more density of states, right? So here's two, you can see the different deuterium atoms. Here's two next to each other, and the calculations tell us that there is one extra electron localized on this deuterium atom underneath. That's what we call the polaron. So it's really localized there, but it can, at room temperature, they can hop from one to the other. But the hopping mechanism is, they hop with a frequency of like 10 to the 12 seconds from one to the next, right? With the frequency of lattice phonons. The tunneling from between the tip and the sample goes really fast, faster than 10 to the minus 15 atoms. So while we tunnel from the tip to while we tunnel into the tip, next electron localizes there, can tunnel out. Next one electron comes there, localizes, and can then tunnel out. Next one come and tunnel out.
Okay. So it doesn't just bind to the vacancy stays and the state hops.
Yes. In fact, you can any electron you put into the system in any way, it doesn't really matter in any way. If it doesn't matter if it's, so yes, the electrons don't seem to care where the vacancy is at all, actually, right? And there's really no correlation between the vacancy and which one, like here, which ones are darker and less dark. And it says actually that the dielectric constant of titanium oxide is really high, so there's a lot of screening in this material. But it's not like one would intuitively think, right? The electron stays there. Actually, the electron goes in, can localize on each titanium atom. For the most part, the most likely hop around, and the most likely position is actually underneath the surface. Okay. Any other question? All right. So we've discussed one image so far. That would be a. Let me just talk about this non-contact AFM next a little bit, and I will start and then maybe continue tomorrow. Okay. So for the non-contact AFM, what we should think about first is the interaction between just two free atoms, okay? Just in empty space. So this is the interaction between two atoms as a function of distance. So here I have, and I can plot the interaction potential. So in this case, it doesn't really matter which one I take, but in this case, it's for, this is out of this paper, this would be for two silicon atoms. So the interaction potential between two silicon atoms. So there's no interaction if they're very far away from each other or very little. Then there will be attractive interaction. So the potential goes down. And at some point they get too close together. The outer shells overlap. There's powder repulsion. There will be repulsive interaction. And then at the minimum here, this is the distance where they will naturally be in a lattice. That's the minimum between the two. Now this is the potential. Then you can take the first derivative over z, and that gives you the force, right? So the force will be 0 at the minimum, at the equilibrium potential between two silicon atoms in the sample. It will be attractive if they're further apart. And then it will be repulsive if closer together. Repulsive if closer together. So this is just the derivative. And then what you can take is the second derivative that Franzi calls the stiffness. So just if you think in terms of oscillating, harmonic oscillation, right? You have interaction potential, the first derivative, the force, the second derivative would be the K, which gives you the resonance frequency. If you have elastic interaction, so if you like a spring between the two. Second derivative gives you something like the stiffness that then has to do with the resonance frequency. So before, the interaction potential typically is in electron volts. So we have about, the binding energy between two atoms is something like 3-4 electron volts in a solid. The force between two atoms is in the range of nanonewtons. And then this K, this stiffness, newtons per meter, is in the range of 150 or so for, in this case, the silicon-silicon interaction potential, just to give you an order of magnitude. Now, As I mentioned in the beginning, we have this non-contact atomic force microscope where we have a harmonic oscillator, which is this tuning fork that swings with its own resonance frequency, typically 20-30 kilohertz. It's a very high quality factor. That means you start swinging and it swings forever. So there's very little damping, which means the resonance frequency is very sharp. We've mounted here an STM tip, a sharp tungsten wire, and we can measure the tunneling current. And then one measures, when one brings the tip close to the sample, one measures the change in resonance frequency. So this is here, this is very schematic, the distance between two atoms, interaction potential, force, and stiffness. Here, then this is more, so again, distance between now the tip and the sample, the change in resonance frequency, very far away, no change, coming closer, bigger change. And at some point you come to the, this is all in the attractive interaction still. So here you still have attraction between the tip and the sample. And at some point you have repulsive interaction. So at some point you get too close. And the tip is modulated. So the way it's done is that the whole sensor, this whole sensor is put in a little bit of shaker bezel, so it's a little bit shook up and down, which changes the amplitude with the amplitude of this tuning fork, with an amplitude of about, between 10, let's say 0.1 angstrom. So you change the amplitude and you measure the change in this frequency change as a function of Z. And depending, so you bring the tip close to the sample. It has its own resonance frequency. You bring it back, bring it closer, you bring it closer. And this is then, so to speak, the set point. So you put the tip here, it changes, you have a little bit less than the resonance frequency. You change the amplitude. And then by changing the amplitude, the signal that you measure is the change in resonance frequency, the DF. So what I've shown you here is the change in the resonance frequency at a certain position in front of the surface. And depending if you're in this position or in this position, actually if you're very close to the surface, very close, so already in repulsive interaction, then you get a very high contrast. So the contrast that I showed you before is really very close to the surface. In repulsive regime, we get a high contrast. And yeah, so in order to do that, what you do is you put the tip in front of the surface, let it change. Some post change, put it at a set point, so you have a change in resonance frequency, very close. And then you start moving. And when you have interaction with the interaction between the tip and the sample changes, you measure the change in resonance frequency. And this is what the signal is that we give in this image. Now, all these images are done in constant height mode. That's why we have mounted the whole chamber on these bungee cords, because this is where the group photo was taken, I showed in the beginning, and this is where our lab is. So you can, the whole building swings with 2.2 hertz with an amplitude of a few microns. So we have to decouple the whole instrument from the building. That's done with these bungee cords. And the measurement is done at low temperature at 4 Kelvin or 78 Kelvin. Okay. I have one last question prepared for you. And actually the question will come up tomorrow, we'll answer tomorrow. So what does one need in addition to a good instrument, knowledgeable people, good vibration by isolation? What does one need for atomically resolved non-contact AFM?
Okay, so now it's on.
I don't think we need 5 minutes for that.
I don't think either. We have only 4 minutes left from our original slot, so I think after this poll, we should perhaps conclude for today and continue tomorrow. I think this one is more. Oh, nobody choosing 10. That's sad.
Okay.
Okay.
So meanwhile, are there any questions before we stop? This is the last.
I will ask a scientific question.
Yes.
Does the theory, I mean, what the modeling group does, is it able to predict this bending pattern which you then see in the experiments? You know, when you detect these delocalized electrons which came somehow out of the missing oxygen atom, right? I mean, there was this very clear bending, right? And so is the theory able to look at the system globally to predict that?
Yes, yes, it is. But in order to do that, they need to make the right kind of approximations. And it's very difficult for them to know what the approximations are. So what we have collaborated with this theory group is to, so in essence, they can, in the CFD calculations, when they put extra electrons, they completely delocalize immediately. And then with something that's called the Hubbard U, you can put it and localize it on certain atoms. And how big this parameter is very difficult to judge. And by being able to see with STM in what conditions it is localized and delocalized, we were able to figure out with them together what these parameters they need to use in order to model it. And then once they had that, the theory and experiment agreed really very well.
And then the last thing also was, doesn't in case of the STM, doesn't the measurement interfere with the data? Because the measurement is actually putting electrons into the system, no?
Yeah, taking it out in the system. Yes, that's true.
Taking it out, yeah.
That is very true. But it does, but it takes out electrons much faster than they come. So it takes out electrons and then the system relaxes. So when you go to a too high, we found when you go to a too high tunneling current, then you really start to stir. So the system can relax much faster than the electron is going, can relax to its state while this tunneling is coming. So, but the tunneling current we take an electron out. Then there is a factor of 10 to the 3 seconds or 10 to the 3 between the different, you have to look at how fast can the system relax and how fast they get an electron out, right? And if the system can relax in between, then it doesn't disturb the measurement. But if the tunneling current is too high, then the system cannot relax. And in fact, this defect state, the position of the defect state that we measure, was actually affected a little bit by the tunneling current that we draw.
Yeah, that makes sense. Thank you.
Okay. All right. Okay. Yes. All right. Well, I'm very happy that 71% of people were awake at the end of my talk. Yes, thank you. Thank you for paying attention.
Including the biologists.
Including the biologist, exactly. Thank you for paying attention, and I see you guys tomorrow.